Hello, welcome to this short presentation. It is about the linear regression model introduced in the related article at finaquant.com. I will now show this estimation model in action. Let's begin. This is the function block in MATLAB Simulink that represents the assumed real-life physics of an athlete who is running 100 meters against the wind with a weight attached to his belt. I use this function to generate historical data. As you see on the block, there are three factors or inputs affecting the performance of the athlete. Wind speed measured in kilometer per hour, weight in kilogram, and temperature in Celsius. I can show you the formula of this function. x1 is wind, x2 is weight, capital T is temperature, and the final outcome is time record of the athlete. Now these input values represent the ideal conditions. 20 degrees, ideal temperature, no wind and no weight. And as you see, under these ideal conditions, the measured degree is 12 seconds. Let's change these input values a bit to increase the level of burden. Let's generate a wind, say 25 kilometers per hour, weight 2 kilograms, and make the temperature less comfortable and see what happens now. More than 15. The third parameter, temperature, is not captured by the linear regression estimation model, and it represents all the unknown factors that add to uncertainty and estimation error. I can now vary the wind factor and generate an XY graph. I add a ramp signal which varies the wind speed from 0 to 40 and run the simulation. Here you see the result. As we vary the wind speed from 0 to 40, the time record is varied from 13 to about 18. So far, so much for the physical function. This is now our estimation model with linear regression. We have two inputs, wind and weight, and three coefficients. The optimal beta coefficients are already calculated and fed into the function block. I will vary again the wind factor from 0 to 40 with a ramp signal, then run the simulation. This is the result. You see wind factor on the x-axis and the outcome time record on the y-axis. Let's combine these two blocks, the physical function and the estimation model, in order to see the behavior of the error, I mean the estimation error. Here you see both blocks in action. The physical function at the top in blue and the estimation model in orange at the bottom. Let's talk about the input factors. A ramp signal again generates values for wind that are varied between 0 and 40 within 40 seconds. Weight is constant, 1 kilogram, and the temperature is a random signal with a mean value of 20. This graph shows the variation of temperature in 40 seconds. Here we have the real observed time record of the athlete as the wind speed increases. Here we have the error as difference between the observed and estimated time. This is estimated time. It's a straight line as expected. And this part, which looks quite complicated, calculates the mean square error, which is now about 3%.